Yeah, thanks so much. And it's actually great to be back. I was here 4 years ago. I visited for a couple of months. It's actually been really fun to see a lot of the same faces. I'm unfortunately leaving tomorrow. But hereby I invite you all to either come visit at Harvard or next, like starting this summer in New York. And always happy to host anyone who wants to give a talk. I also thought since this is like kind of like the first talk like of the summer, like everyone is probably still a bit like, oh, getting back into work. I thought like to flip it a bit around, and I have like some fun things I'm gonna try out in the colloquium. So bear with me. It's maybe a bit different from a standard colloquium, but I'm hoping also to highlight a little bit of like what people do here and so on. And maybe more introduce problems than solutions, but we'll see how that goes. I always like to start actually by highlighting some of the students I have the honor to work with that really make a lot of the work so much more fun. And you'll see some of them like come back like during the talk, but they're all not here, so it's sometimes nice to see the faces. Okay. So I think this is an extremely exciting time to be alive and like working on astrophysics, and especially to be here at Monash and do gravitational wave science. And that's because I think we're really at this like tipping point where we're going from just like a few events that LIGO have observed now so far to this new era where we're going to have like many thousands or tens of thousands of detections. Yeah, so this is a picture that shows what I was saying just in words. So actually here in like thick lines, you can see all the detections that like LIGO has observed so far in like a cumulative distribution. So right now we're here. LIGO and Virgo is not running, but we have about like 100 binary black hole detections, and then 3 black hole neutron star, or 2, depending on how exactly you count, and 2 binary neutron stars. But I think the most exciting part is this dashed line part, where we see like, in just a few years, so we're actually going to go towards this like new era, where we're going to have like thousands or tens of thousands of detections per year. And this is especially true once we go to like this era of like next generation detectors, such as Cosmic Explorer, where we're really reaching this like millions of detections per year if everything works out. Now this is exciting because not only it basically means like our field is exploding in just total number of detections, but besides just like more detections, there's something other that's like very, very exciting. And that is that these gravitational waves actually provide a really good probe to probe massive stars throughout cosmic history. And the idea of like why gravitational waves are good is that because we think they form these gravitational wave mergers, like stellar mass black holes, like once upon a time formed from like pairs of massive stars. And they maybe form a double compact object here, like say a black hole and a neutron star. But the time it can take for such a system of 2 black holes or 2 compact objects to actually spiral in and merge can take anything from like a few million years to like many, many giga-years. And so even the events that like LIGO, Virgo, and Kagra are seeing today, because of this like wide span of merger timescales, already probe like massive stars and these black hole systems like throughout the entire cosmos. And the exciting part is that like with these future detectors, we won't only be able to see local things, but we can actually like kind of probe these gravitational wave signals and properties like all across our universe. And so really understand how black hole and neutron stars like pair up, how they merge, and how this changes as a function of redshift. At the same time, it also kind of naturally results in one of the biggest open questions, at least in gravitational wave astrophysics today, which is how these systems actually form, and what like astrophysics or physics can we like learn from these detections. Okay, and so for the first questions, how do these systems form? There have actually been a lot of theories out there. Like usually we like to come up with a lot of theories of how these work, and we actually currently don't know yet what the answer is. And so currently some of the options include what we call like in the field. So maybe they form from pairs of massive stars, as I mentioned, that start very wide, but then later on during mass transfer can get closer together. Maybe it's from these population 3 stars that are very low metallicity stars. Maybe chemically homogeneous, that they form very close at low metallicity, but they can stay small. Or maybe even in triples or multiples. Then there's also this kind of like second category, is that maybe instead they form in these dense stellar environments, such as globular clusters or young and open star clusters, where the black hole and neutron stars can undergo like many, many interactions before they eventually merge. And then there's also some other channels that already don't fit in these 2 categories, like maybe they form from primordial black holes that formed really, really early on in our universe. And over the years, or over the past 5 years, I think something that we already learned from theory is that actually the picture isn't even as clear as this. Like you have a lot of combinations of channels, like, oh, triples can actually also exist in globular clusters, or binaries can exist in those systems. And so we're already starting to get like a quite messy picture of like what formation channels are out there. And so, people like me, but also other people who study this, we will go to conferences and colloquia, and then we all have like our own favorite theory. And so what do we do to like find out who is like right, or like which of these formation channels actually explains the current observations? Well, so we sometimes fight or like argue at these conferences, but kind of the main method that you can do to try to verify some of these channels is that you actually want to compare the gravitational wave observations. So for instance, the masses of the black holes and neutron stars that we see merging with LIGO, Virgo, and Kagra, and their rates and their properties. And you want to compare that to these expectations from these formation channels. So basically what you do is you run a population synthesis simulation where you model these globular clusters over time, model the stars, find their gravitational wave sources, and then compare to data and see whether your model explains the data better than other models. Now, if there's one thing you need to hopefully take away from this talk is that, in theory, this is perfect. So in theory, we really want to like learn from gravitational waves about like these massive stars and how they were formed and when and where they were formed. But that in practice, we are dealing with this, what I call the uncertainty challenge, where there's so many underlying uncertainties in these models that make it currently like impossible to explore them all, and thereby truly like fully understand and explore the parameter space of these models. And so for that reason, we cannot draw any strong conclusion at this moment from just like small explored parameter space. And so that's very challenging. But okay, I thought maybe, especially since lots of people here work on this problem, maybe it's like actually a nice occasion to like learn a bit more about like how do you do this modeling. So if you have your favorite formation channel, how do you actually go and model gravitational wave sources? Okay, there's basically 3 steps that are always involved for gravitational wave sources. So the first one is that somehow these, as I said, all these gravitational wave sources could have formed like really throughout the entire universe. So the first thing that we need to do is we need to somehow have a model for our universe for like how many stars it forms as a function of time, and with what metallicities they form, because metallicities turn out are very important for kind of dictating how these stars evolve and how they end their lives. And so this is often called like the cosmic modeling, or basically making a mock universe. And so what people do is they either employ analytical functions, they base it on cosmological simulations like Illustris, or almost directly from observations, where they try to find some model, some cosmic model that just tells you how many stars form as a function of time, and with what metallicities do they form. The second step is, now that we have like a uniform universe that makes these stars, we need to find out, okay, if we have a star system, which of these pairs of stars, for instance, forms a gravitational wave source that we could detect today? Because actually the majority might just like disrupt during a supernova. And so for this, we have models like COMPASS that a lot of people work on here, where basically you can input a binary system, star system, with certain properties like masses and separation. And then COMPASS takes into account like the single stellar evolution, but also binary interactions that the star can undergo, such as like stellar winds, mass transfer, supernova explosions, or this like common envelope or unstable mass transfer phase. And then it decides at the end of the simulation whether this star system with these initial conditions formed a gravitational wave source, in which case we're happy because we can compare it to data, or whether it forms something else. And so actually in the majority of cases, it just like disrupts and forms something completely different. That's step 2. And then finally, step 3 is, okay, even if we have this entire universe with stars, and we evolve these stars to see which ones form gravitational wave sources, then even if things merge, we still need to like find out which of these merging sources can we actually detect, or would LIGO, Virgo, Kagra detect. So at the moment, probably like beyond redshift 1.5 or 2, we wouldn't detect these systems, and so we only see a part. But this part is actually relatively easy, as it's somewhat well known what this like sensitivity of gravitational wave detectors is. Okay, so here comes the fun part. This sounds maybe simple, but this is a really, like these 3 steps are like a really important part for like understanding our models, but also understanding like why people like me and Ilya and like Reinhold gets so excited about using gravitational waves to study massive stars. And so I actually wanted to do a little bit of an experiment. I need about like 12 volunteers who maybe want to come forward and actually run a simulation with me. Yeah, I need 12, so you know, like more than one person. And I'll give you a card, and I'll explain what you'd have to do.
Thank you.
There you go. Few more. I have 2 more. This is the most fun part, so. All right. So I am an astronomer, and I really believe in this like simulation that they come from pairs of massive stars. So now I'm going to run a simulation, and so that's actually what I'm doing right now. So the first step in my simulation is that I need to like, you know, make a cosmic model. So I need to like populate my universe with stars. Now I've done it already. Like I've given each one of you is per now, congratulations, 1 binary star system. And so the first thing I need to do is like need to give every binary star system kind of a redshift. So like at which place where you formed, like where in the universe do I make you like formed in the universe. And so what you can see, if you want, you can hold up the card to like the audience, is that the card will say I'm a binary star system born at redshift and a certain number. Now behind you, I have an axis, and I'm going to ask you to organize yourself along the redshift axis that you'll see on the x-axis. And if you have the same number as someone else, to stay in front of the other person to make kind of like a queue. Yeah. Yeah, so the early universe is here, 8. Then we have 6. See how it works out? Yeah, and if you have the same number, try to stand in front of each other. Yeah, make like a queue. Yeah. You have 2? Okay, can you hold it up to see? Let's see if everyone. Okay, 4, 2, a lot of 2s. I have the 0, that's why. Okay, so, you know, does this look familiar at all? Like how my binaries are distributed across the universe? Is there something that you recognize from this for how I distributed them along redshift?
Peak of star formation.
Peak of star formation? Where is the peak of star formation? 2. Is that where my peak of star formation is? Sure. Maybe not on log scale. Yeah, so actually, like, if I were to make a histogram of all my data points, which, you know, in real life, I would have to, like, ask you all to, like, maybe stand on top of each other's shoulders. I won't do that here because the roof is somewhat small. But what you would see is that, you know, I have about 5 data points here, maybe 3 here, 2 at redshift 6, 1 at redshift 8, very lonely Reinhold. Sorry, Reinhold. But it would actually, you know, if I were to do it correctly in my simulation, it would actually follow this distribution. If you want, you can duck a little bit, which is the star formation rate. So you know, if I were to do this with a large sample, I hopefully would get something like this, a star formation rate of stars. OK, that's great so far. However, this was just step 1, right? So now I've distributed my binaries. Step 2 is that I need to find out which of these binary stars actually form a gravitational wave source. And unfortunately, although all of you are awesome binaries, not all of you become awesome gravitational wave sources. So what you can do is you can flip around your card, and that's actually like the compass simulation. And I have like run for you whether you become a binary or not. So, and if you haven't become a binary, you have a cross, you can go back in your seat. If you have a check mark, you're all good. You can stay. It's OK, yeah. You can. Thanks. OK, and can you now flip your card to like show the redshift again to everyone? Yeah. So what do we see? Like, is there anything you notice about who gets to stay and who gets to leave? Open question.
The older ones?
The older ones? The older ones get to stay, yeah. So if you pay attention, you see that the majority of like stars that were formed early on in the universe, a larger fraction of them actually formed in my simulation binary black hole systems compared to systems on the left. So a lot of these redshift 2 systems are left, and only Avi is still here as like a strong redshift 2 binary making a gravitational wave source. Is this something we expect? Like, is there a reason why my simulation might say I'm more efficient at making gravitational wave sources early in the universe than late in the universe from pairs of stars?
They just have longer to evolve.
They have longer to evolve, yeah. So maybe if they take really long to get there, they have longer to evolve. That's something, yeah. Metallicity, yeah. So metallicity is a huge thing. So we believe that, or we are pretty sure that stars here are typically born with a lower average metallicity. And that means that they, for instance, lose less winds during their lifetime. And so they can stay more massive. And we think overall, from our simulations, but also from theory, that binaries with lower metallicities are more likely or more commonly form gravitational wave sources like pairs of black holes. OK, this was step 2. We're happy so far. Step 3 is the most difficult part for you as my experiment. Yeah, it's a bit technical, but we'll get there. The last part is like, OK, this is just where these gravitational wave sources have formed, like where the stars formed, and then pretty quickly, within a few million years, they form pairs of black holes. But this is not yet where you actually will merge and where you might be able to be observed by LIGO. So the next step that we have to do is that if we have these gravitational wave sources, we actually have to kind of add the extra time that it takes for these binaries to then become like a merging binary black hole. So there's this delay time or spiral time. So I've calculated for you this too. Like on your same card, Compass can calculate this like delay time, like how long does this take. And now it's the complicated part. So you know your redshift, but then you have to add how many gigayears delayed you merge. And so they've given it in gigayears, so that's like why it's a bit challenging. And you have to move that to the left. So Tegan, where did you start at redshift?
At 4.
4, and then how many?
6.
6. Okay, so there's like about around 7-ish. Yeah, and if you want, you can hold again your redshift number to the front. So you can see like it's complicated, right? So the answer is not the same for everyone. Some of these binaries or pairs of black holes might have very long delay times, and so merge much further away to the right. And some might have like very short delay times and very close to where they were born. But if I'm now an observer, so say I am LIGO Virgo Kagra, I'm on this side, I'm at redshift 0, and I'm looking into the universe. And maybe with current LIGO Virgo Kagra, I can see up until redshift 2. So I get like the first 4 data points, and then maybe here I have to make a cut. So I would only see this part, right? And then maybe with future detectors, I can actually see everything on the left. But you can already see that even if I see systems here, I actually see things with lots of different, that were formed at different redshifts. So like redshift 2, redshift 8, redshift 4, redshift 6. So on one hand, this is super cool because it means that even observing things locally, I can really probe massive stars like all across the universe. But at the same time, this is the challenge because now I have to figure out from just a few detections, like, OK, which stars were they actually formed from? And like have to really model this entire universe to come up with these like few systems that I can actually detect today. Thank you. So I hope that's clear, and I hope, I know this like it takes always some fun time, but this is really like a key aspect of doing these simulations. Like you really have to model the entire universe, and you end up with this weird mixture of things that kind of formed from many, many different formation channels, different metallicities, different redshifts, which is really what the challenge is. But if we somehow can figure out and like unpuzzle that story, we can really like do really cool things about learning about these stars that are really far away, and that there's just no other way to observe stars at such high redshifts other than in this like indirect way. OK. So now, this uncertainty challenge, where do we stand today? And I wanted to give an example of merger rates. So one thing that one can do is like for all these different formation channels, we can do the same experiment, have this like mock experiment or simulation where, based on either they form from pairs of massive stars, either they form in globular clusters, you do the same picture. You model the stars, like where they form across the universe. You have a cosmic model. Then you add this simulation to calculate where do they merge. And then you can calculate, OK, how many would LIGO Virgo Kagra like detect today? And this is something that people have done for like many, many, many years, like more than 10 or 20 years at least. And something that we recently did is that Ilya and I, for a review paper, actually try to like summarize, review a little bit where this field is and what these expected merger rates are. So here on the x-axis, what you'll see is this is the local black hole merger rate density. So this is just how many black holes are merging in a gigaparsec volume around us per year, so per time units. And this axis, it's going to like flip through all these like different expectations and observations that we know now from the past 10 years. So the first one, and you see it's log scale, so it's like quite dramatic. So these first 4 data points are between 10 and 100 black hole mergers per gigaparsec cube per year. And this is actually what we know from LIGO. So LIGO can see these 100 detections today. And from these 100 detections and knowing its volume that it's sensitive to, it can infer that it must have the local rate must be somewhere between 10 and 100. And there's a little bit different assumptions that you can make about the black holes that you don't see. But then eventually you based on these different assumptions, you get these 4 different estimates. And this is what LIGO comes up with. Now, how about theory? Well, OK, let's look at that. So now as we're flipping through this video, these slides, it's basically flipping through all these different formation channels. So green is just they come from pairs of massive stars. This is they form chemically homogeneous evolution. Each horizontal line here is one paper or one study that tried to do this entire modeling, so this entire simulation, and then try to calculate this merger rate from theory. For a horizontal line, you sometimes see different data points, different scatter points. So that means they done the simulation, they get a rate. And then they redo the entire simulation, but changing one of their physics assumptions in their model. And so what we did is we wrote this down, but then connected for the single paper simulations with these different parameter expectations. And so the horizontal line kind of gives you an idea of the range of expected rates that came out of that study. And so this might not seem like a lot, but this is basically, in these few minutes, if you pay attention, you're basically reading through about 250 papers. And this is each paper is probably one PhD student or someone really working for a year, understanding these simulations and calculating this. So it's quite cool. There's kind of 2 things that I hope you also notice. So first of all, that a lot of these merger rates span enormous ranges. So you can even see that within one study, often it can span many orders of magnitude. But that also, already from these comparison, you can see that it's actually really challenging to rule out one of these formation channels when just comparing rates, right? So our goal was OK, if it matches the rate, great job. If it maybe doesn't match the rate, maybe you could say, OK, not this channel. And one thing that you see is actually in the majority of cases, there's always some simulation that still spans the observations. And so it's really challenging to just rule it out. And this gets worse, actually. So another thing that you can do is you can just focus on one of these formation channels. So in this case, OK, let's say they come from pairs of massive stars. And then you just ask, OK, if we just look at rates that all kind of align with the LIGO-Virgo-Kaga rate, so these are already models that rate-wise overlap. But then you just ask a question, OK, so all these pairs of massive stars that then went through evolution and then formed the gravitational-wave source, how many of them, for instance, underwent this common envelope phase that we think might be really key to these simulations? And this is this unstable mass transfer phase that is quite mysterious. So a lot of people hope to learn about these phases from gravitational-wave sources if they are really key in forming these systems. But then if you ask this question, for these simulations that almost predict the same merger rate, you get very different answers depending on the simulation. So here's just, again, a range of simulations from literature. And these orange and blue bars basically indicate whether the system underwent the common envelope, yes or no. And so you can see that whether these systems and gravitational waves can probe common envelope really depends on who or which model you're asking this question. And things get worse because it turns out that even how our rate, so this is kind of your merger rate of binary neutron stars, and whether that rate goes up or goes down as a function of some of these uncertain parameters in our models, really again depends on which model you're asking. So if you look here, then compared to a alpha as 1 value, sometimes the merger rate goes up and sometimes the merger rate goes down. And this is because all these models turn out depend, a lot of these parameters are correlated. So also Tegan actually did some cool work recently on this. And yeah, so if there's 2 things I hope you remember and that are very pessimistic is that, only very few of merger rates can be ruled out just based on comparing these rates alone, which is the thing that most people have been doing over the past 10 years. And second of all, that a lot of these merger rate and calculating this is really uncertain and really depend on a lot of these underlying uncertainties in the models. And so to give it a bit of an example, there's lots of things out there that are in these models that are not thoroughly known, such as stellar winds. even a fraction of binaries or initial conditions. Things like supernova and supernova kicks, and especially also mass transfer that many, many people work on. And so on top of this, these simulations actually become computationally expensive just because you have to really simulate like all these stars across like the redshifts, and very few of them become gravitational wave mergers. So we can just simply not model them all, and that makes this like challenge so challenging. So, that being said, you might wonder, with so many uncertainties, can we learn anything from gravitational waves about stars? And so I like to think of this like, okay, you're trying to make an error bar, but just like adding error bars, and it just like doesn't stop. And I truly understand if a lot of people are pessimistic. I tend to be more on the optimistic side. And I would say it is possible, but we have to do some extra work. It doesn't come as easy as we maybe hoped. So what now? And so I'm just going to mention a couple of things that I'm also working on and like other people are working on to kind of overcome this. But this is especially the part where I'm like, oh, it would be super, super interested to hear thoughts from like this audience of like what things might be promising ways to kind of overcome this uncertainty challenge. Okay. So the first thing is that I think it's really important that we, first of all, start to investigate and quantify how some of these uncertainties impact our model outcomes. And so here's, for instance, some work that I've done that shows that, if you vary stellar evolution, so here you go to the right, or vary these like assumptions for the cosmic evolution, so how you populate your stars in your universe, you get very different merger rate predictions. So this is for black hole neutron stars. But you can kind of start seeing some trends, and you can start like quantifying about which of these uncertainties matter more for like impacting these kind of quantities. And so here you can see, that there's different types of uncertainties in the stellar evolution. So for instance, these are models where we varied like supernova models or common envelope evolution, and they impact the parameters differently. And most interestingly, this behavior might actually be different for binary black holes, which is shown here, where you see like an almost more flat distribution, meaning that it's much more sensitive to like how many stars you form and with what metallicity they form than maybe some of your stellar evolution assumptions. And you can do the same for binary neutron stars. And again, you see kind of like different sensitivities to certain parameters. And these different behaviors for these different flavors is also due because how many binary neutron stars or binary black holes you make depends on like your metallicity. So we already said like early on you might be early on at low metallicities, you might be much better at making binary black holes than at solar-like metallicities. But this behavior is like different for binary black holes, where you see this steep decrease, and that basically at solar metallicity it might be very challenging to make binary black holes, whereas for binary neutron stars it might be more flat. And so this leads actually in those former plots to like this different behavior to different assumptions. And so one solution might actually be that, instead of looking at just like one flavor separately, what a lot of studies do, maybe we can actually like see which models kind of like simultaneously can match like these different merger rates from different flavors. Okay, but there's more. So another thing is that so far I only spoke about like the merger rates, but we have much more information by LIGO. So one of the other important quantities is to really look at like the merger shapes. So for instance, here's the chirp mass distribution, this like funny black hole and neutron star mass distribution in this case. And again, like all these different parameters have very different impact often on like what black hole masses or neutron star masses you expect. And so that's extra information. Another thing that LIGO measures somewhat well, and especially in the future we'll have much more data for, is spins. And so some of the projects I've been working on with Eric Thrain and Simon Stevenson here, and many people here at Monash have done work in, is to really think about like how can spins help us inform about these formation channels. And for instance, this like recent study is like, okay, which black hole is spinning? Can that tell you something about the formation history and like mass transfer and physics history of the system? I'll skip this for now, but I'll just say that there's like some really, really interesting work, including from Shanika, who is here, and like many other people, where, both from observations and theory, we try to like think about what fraction of a black holes do you expect to be spinning in LIGO, and are things aligned with what we expect from theory versus observations. So I think it's there's an interesting debate going on, and I think 04 and 05 will actually help us a lot here with more data. Then the other thing is also like, so far we've looked at these like local merger rate or densities, but there might also be differences in like how many binary black holes you form as a function of redshift. And it might really depend on formation channels. So here was a nice paper from Ken Ning, where he basically said that these formation channels might have very different behavior of how many binary black holes you find as a function of redshift. And so once you start observing deeper with the Cosmic Explorer, you can really see until like 7.5 redshift. You might be able to actually like distinguish between channels based on their redshift behavior. And so Adam Bowski is like one of the students doing a lot of work on that now. But I also want to caveat that in these type of studies, it's often like, okay, you have these 3 different channels that I also plot here. But each of these channels, again, have their own uncertainties. So realistically, this is going to look something like this, where you just don't have one pink model that is like massive. They come from massive pairs of stars, but you have actually a range of models that might be equally likely to expand this. So in practice, we're actually dealing with a picture like this, where you can already see it becomes a bit more challenging to learn about formation channels just from the rate alone. However, there's like more interesting things. So one of the things that also I think a lot of Monash people are thinking about is to also include constraints from like electromagnetic counterparts. So long gamma ray bursts, but also transients such as like core collapse supernovae or other things like type 1a supernovae associated with this. And so also Reinhold is actually finishing a paper that will be out soon that I think will really contribute to like helping us further in this type of picture. And people have done similar work, and like you can also look at other surveys, like some of these binary neutron stars or black hole neutron stars might also be pulsars. And then you can also even look at other gravitational wavelengths, such as like LISA, where in the space-based gravitational wave detector that will be built in about like 20 years, hopefully, they might also show up, and it can tell us something about these constraints. Now, in addition, there's a huge effort, and actually also a lot done here at Monash, which is why I want to highlight it, in like actually improving the computational costs of these simulations. So there's many new cool like machine learning and AI algorithms. And so, for instance, I've also worked with Ilya and others on one of them, which we called like stroopwafel, that basically, with the same number of samples can like much more efficiently, so same computational cost can like much more efficiently find these gravitational wave sources in simulations and like model them. And so this can reduce, again, like computational cost by like factor 10 to 100 or 1,000, which then means you can kind of like run, hopefully, like another 1,000 like explorations. And so at least the things that are uncertain, like maybe you can start really exploring them. And there's been some really cool recent works also with normalizing flows. And Ilya and I did something with like uncertainty quantification that, there's a lot of development in this field where we're hopefully making some progress in doing this. And then, a big issue is that also we need to improve many of our stellar evolution codes. So I'll show you the meme, but this is like, all modern population synthesis codes, so all these codes that model these gravitational wave sources, typically rely on this like one code from the 2000, this like famous paper that's like Hurley's SSE or BSE paper. And so we kind of know that it's not 100% correct or far away from 100% correct. And so I think it's really important that we start to kind of like test and make better models for like some of our internal stellar evolution. And so I also wanted to highlight Rio's work, who's, for instance, been thinking about how can we better model some of these like mass transfer phases and physics inside of codes. And then last but not least, there's also a lot of effort going on in, using this opportunity to to compare codes and like understand why some of these codes with different assumptions like give such like different results. And so there's, for instance, Poojan Agarwal from Swinburne was like a recent paper where she kind of like explained some of the differences between codes. But there's also a big project now going on where people are trying to compare double white dwarf populations for LISA based on like all these different codes that I encourage people to join. But I think none of these are perfect, and I think actually the true answer is like we need you, like everyone here in the room as well. Because I think a lot of the improvement of really utilizing gravitational wave data for learning about massive stars is going to rely on, a lot of improvements from different fields. So, we need to both better understand our gravitational wave sources, but we also need to better understand like the enrichment in our universe and like how stars formed and died and with what metallicities they formed. So, using new observations from GWST, better understanding galaxies, better understand that like cosmology and star formation is going to be like crucial to help us kind of like minimize uncertainty where possible, and reduce this uncertainty so that we can truly like start learning something instead of just having a pile up of these uncertainties. And so this is definitely challenging. You might leave this room and be like, okay, I'm utterly depressed about this field and the opportunities. But I wanted to remind you that this is, it's challenging, but it's going to be really worth it. And that's because of this picture where, okay, now we have 100 detections, but this field is exploding. And we are going to this like new era where we have, millions of detections per year. And so if we manage to unpuzzle this puzzle and like truly understand some of these uncertainties are coming from, I think we're gonna be in this like super rich era where we can then use these gravitational wave simulations to learn about these stars and the formation, lives, and deaths of these stars that just in no other ways or means is like possible. And so I think it's really worth it. But I wanted to remind you, like, I think right now we're not there. And I think the first step to like going there is really like tackling this uncertainty challenge and like minimizing and understanding where these uncertainties are coming from and trying to see how we can do this better. And so with that, like in maybe the last 2 minutes, I wanted to share like one small other note on uncertainty, which is that, uncertainty is not only common in these models, stellar evolution models, and science, but I think it's actually, I've come to learn it's actually also very common in just the lives and like professional careers of like scientists, so, astronomers. And, personally, I think it's very important for like, especially early career astronomers to like learn how to like navigate the academic system in like permanent evolution. So think about pandemic, climate change, like political crisis. But this can be very challenging. And I just wanted to like share that something that I've learned and like read a lot about is that like especially underrepresented minorities and especially multiple marginalized minorities such as women of color or LGBTQ pan-gender minorities, we now know like from many studies that these groups face from early childhood through universities most barriers like in their academic path, including like things like harassment, anxiety, and discrimination, which we know like leads to their structural exclusion from our community. And so, this is something that's close to my heart, and I personally really believe that like us as a community, it's not only important to like understand uncertainties in these models, but also to understand these uncertainties in our own careers and like to try to come up with like support structures to help people. And so I like to see this as this like tree that Serena Vincent-Quera made this picture. We're like, in the end, we're all trying to get to the top of the tree where, which includes like doing awesome science, doing some cool observations. But the path towards there might be very different for different people. And so, I really see like our role as, being part of this community to be like these hands that help to like put support structures in place that can kind of help people to, support them to get to the top of the tree and do awesome research. So I have maybe 2 takeaways that I want to add in that sense. So the first one, 2 things I would say these are things that I think we can all do, which is, the first one is like, I think these events that support and can help like early career astronomers can be very helpful. And so I actually, together with many people from Monash, organized a bunch of them, including at the EAS in 2023 this summer. And so, please join us. If you have anyone who can host cool workshop speakers, let us know. We're currently looking for things. And the second thing, among this is also like, you can look around you and think yourself like, how can I include or organize like things or events for like early career astronomers, such as some of the groups that are here at Monash. And second of all, there was this like beautiful report that also showed from research that it turns out that like faculty or in general interactions can have a powerful effect on student retention in or departure from the field. And so students' sense of belonging increases with the number of faculty or just people in the community who get to know them as individuals and demonstrate support for their success. So, something shows that just like how much anxiety people have, or like how much they feel like they're welcome in this group, like it really scales a lot with like how much they feel the other people know them and they get to like have these opportunities to speak up. So, maybe as a fun goal, try to get to know one new person every now and then, and it can really make a difference in this field, as studies have shown. With that, I won't bother you anymore, and I'll take any questions.
So you talked about how the binary black hole rates and the other traits depend on this convolution between your medically specific star formation rates and your binary evolution. It sounds like you're convolving a lot of things that have all their own uncertainties in them. Are there other approaches that you can use to help isolate different things and kind of build up more robust science on the way to getting better rates for your binary compound objects?
Yeah, so I think, and as you already said, right, like there's basically between when a pair of massive stars is formed to when it forms like a gravitational wave source, there's a lot of other phases in between that the binary experiences, including mass transfer, supernova explosions, things like this. And so having data on that and kind of comparing that with like these intermediate stages in our simulations will be really helpful. And I think on top of that, just like having data of star formation histories in our universe will be very vital to push this field. Yeah.
So you mentioned your work about spins, but what's like the key piece of information that you can extract from spins that you can't from just other distributions?
So what things you can expect from spins, from spin data compared to other distributions? So there's a couple of things. So first of all, I think spins are a bit special because there's more convergence, that we think these formation channels predict very different spins, whereas we think they predict much more overlapping masses, for instance. So for instance, we think maybe to get really high spins, like a black hole spin that's almost maximum, you kind of almost, for instance, need like chemically homogeneous evolution. We think these dynamical encounters often lead, like if they merge two black holes, that they might actually lead to the spin of like around 0.7. So these are kind of like more expected predictions. And then there's also a lot of like correlated things that spin. So we think the spin and the spin angle of binaries has very different predictions for different channels, where in some cases we think they're more aligned, some cases they can be random. And then also things of like spins correlated with mass. So which binaries do make spin, do we think is very different. And so for instance, we showed that like, if you believe a certain spin model where you think the black hole in these pairs of massive stars can only spin up through tides, that it basically means that like whether you see the more massive black hole spinning or the less massive black hole spinning in LIGO actually tells you something about the mass transfer history, because it tells you whether they've flipped in masses or not. Yeah.
More questions? I think we still have time. Maybe I can ask more of a philosophical question, if I may.
Yeah.
So I think initially you kind of try to categorize like each channels to like different pathways, either as a binary, triples, nuclear clusters, etc. But you also mentioned that there's some kind of overlap between them, and also at least to me, for me, triples are part of dynamics.
Yeah.
And also in nuclear star clusters, you have the stellar cluster, you have the AGN disk, which have different observables and different physics input. So I'm just wondering, is there any way to distinguish these channels somehow? Because I don't think it's like one channel, and we also like run maybe a population model of as a binary or a model of AGN or whatever. But do you think we should kind of move to like running like models of models?
Yeah.
What are the different weights of each model which they contribute?
Yeah, I definitely, that's a very good question. And I definitely think on the long term, it will be interesting to see, like we should make one universe with like one set of physics that, hopefully some of this physics is the same for whether you're in an AGN or in a globular cluster or in a binary. Of course, it's very challenging because they all have, their own modeling, their own resolution that they require. So that can make it difficult to bring them together. But I definitely think we should like start thinking about, if you were to put binaries or say triples in these other environments or the other way around, like, is it gonna like drastically change your outcome? Like, does it have a significant impact on these channels? And if so, you should definitely care about like including them. If not, then you should still, think about like, okay, maybe I model my things, but I should like add on top of that like some independent model that models like the other formation channel. So it's something that people have been moving towards, but it's challenging.
Okay, thank you. Any more questions? Well, if not, then let's thanks Laura again.
Yeah, thanks so much.